Okay, so this is Tane, and today I'll be talking about different types of stars. And today's video will be covering more of low mass stars. So there are two types of stars, low mass and high mass. But this is part one, covering low mass stars. Okay, so the first type of star that I'll be talking about is called a yellow dwarf. It is the first category, it's the first type of a low mass star. It's a newborn low mass star. These stars are quite rare. About 7 to 8% of all the stars in the universe are yellow dwarfs. And a very good example of a yellow dwarf is the sun itself. As you can see on the top left, a sun is a yellow dwarf star over here. Yeah, right there. With temperature of around 6,000 degrees Celsius and, of course, one solar mass, which is equal to the mass of the sun itself. Um, so, yeah, and the sun is a very balanced type of star. As it is a low mass star compared to other stars like the high mass stars and all other stars, sun is actually quite small. Even though it looks like it's a very big star, sun is actually quite a small star. And yes, one cool thing about yellow dwarfs is that even though they're called yellow dwarfs, they are actually white in color if you look at them in space. That is probably because of their quite high luminosity, which makes them shine very bright. Also, in yellow dwarfs, there's a very high fusion of hydrogen because hydrogen is abundant in their core mantle surface. So there's plenty of hydrogen to burn. That's why they are actually quite hot for their class, for their low mass star class. These stars burn a lot of hydrogen converted to helium, and then helium gets converted into other elements as it fuses. So yeah, a lot of energy is generated from these stars, as of course they're young and they have the most amount of fuel available. So if we go into the sun with, let's say, 2 times the speed of light, we can see the structure. If I remove HDR, okay, we can see the surface properly. And yeah, we can see many of these sunspots, also known as corona. So yeah, many of the yellow dwarf stars are famous for having this. And yeah, a lot of radiation, a lot of solar flares are also given out from these areas. One one sunspot is 2 times the size of the Earth, which makes them very unique. As you can see, this surface, yeah, very bizarre. So yeah, that is low mass stars yellow dwarf. So the next type of star that we'll be looking at is known as a red giant. Now, as the name suggests, red giants are the successors to yellow dwarfs, and of course, this means this is the sun's fate. It's the sun's future. The sun will eventually become from a yellow dwarf to a red giant. Now, red giants, as the name suggests, are obviously red in color, but because they're red in color, their temperature is also between 3,000 to 4,000 degrees Kelvin, much lower than the temperature of yellow dwarfs, which is around 6,000 degrees Kelvin. Now, their size, because they're giants, their size is much, much larger than yellow dwarfs. Um, Red giants are so large that it is proposed that when the sun becomes a red giant, it will swallow Mercury and Venus, and possibly Earth. If the Earth is not swallowed, then it will become like a new Mercury, the closest planet to the sun, the red giant sun, and it will be very scorching hot, very very hot. No life can be can exist over there at that point in the future. Yellow dwarfs live for 10 billion years, and but red giants live for only a few million years. And if you look at the scales of astronomy, okay, normally it looks like a few million years is a long, long time, which it is. But in the scales of astronomy, it is a very short time. It is a very short lifespan for a red giant. But in this lifespan, they are very, very bright, and they're so dangerous. They're so their effect is so large that it is very hard for planets to exist. Now, what you see revolving around this red giant star Aldebaran, as you can see on the top left, star is Aldebaran A. This is not a planet. It's actually a binary star system, and it's its partner here, Aldebaran AB, another star. But this one over here is the red giant, Aldebaran. So this is obviously one of the brightest stars and one of the biggest stars ever discovered. So yeah, red giants, although low mass, not even high mass, although they're low mass, they have many cool properties. Yeah. Apart from that, one more interesting fact about red giants is that, for example, when the sun becomes a red giant, it will become so large and eject so much mass that Mercury and Venus will be completely swallowed by the star. Sun will completely swallow Mercury and Venus, and it is also possible for the Earth to be swallowed. And even if Earth is not swallowed, it will become the new Mercury, as because it will be the closest planet to the sun, and there'll be no expected life. Everyone will probably die. So yeah, it is the sun's fate, and the sun is already 5 billion years old, so it has another 5 billion years to live as a yellow dwarf before it becomes something big like this red giant. Now, if we just go inside red giants, like them just going, oh yeah. Also, what you see happening over here, like I've increased the time speed, and what you see, this gaseous-looking thing, is actually the mass being ejected. They eject a lot of mass, which into outer space, and this leads. This has a connection with the next stage of the star. But anyway, I'm just going to go inside this star, and we can see first of all how bright it is. If I just remove the HDR, you can see these patterns. Now the simulation cannot make them look proper, but you can see that it's not completely spherical. It's just all the okay. So the next type of star is known as white dwarfs. So this stage happens after the red giant sheds all of its material. It sheds all of its material to the degree that only the core of the star is left. That core of the star is very, very hot, temperatures of up to 1 million degrees Celsius sometimes. And this core is the new star. It is the white dwarf. So basically, the core of the star, the remnant of the star, is becomes a new star, half dead, you can say. Now, what we see over here, if I increase the speed also, is not actually a white dwarf. It is a high mass star, which is for part two, where you can see how brightly it's going. But if we look at its partner, it has a partner. It's a binary star system. If you look at this one over here, Sirius B, this one is called Sirius A, the main star, but this star is a white dwarf, and it's called Sirius B. Um, it's a very, very bright star. Temperature is 25,000 Kelvin, which is very, 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 very bright, very, very hot. So this shows that oh, it's rotating very fast. Initially, this was a normal yellow dwarf, which later became a red giant, and now this is the core of that star. This is how the core looks like. So yeah, fully blue, and blue means a very, very hot star. So yeah, that is white dwarfs. White dwarfs are not that abundant in the universe because not all um, stars have been old enough. Not many stars have been old enough. Or yeah. Okay, so the next type of star is actually my favorite class of stars, favorite type of star, and this comes after white dwarf. After a white dwarf takes billions of years to cool down. This is the next stage. And it's actually very well researched because these types of stars are the most abundant in the universe. Around 75% of all stars in the universe are red dwarfs. So red dwarfs are well studied because, of course, there are many of them, although very dim, because now the temperatures of a white dwarf have cooled down, and it has come all the way down to around 3,000, 2,000 degrees Kelvin. So although they are hard to spot, there are just so many stars that all the stars near the Earth have been able to be seen with good telescopes. And this is one example, around 30 light years away, Pt.1. Now, what makes this star so unique is, of course, um, how light it is in terms of its conditions. Because this star actually has real planets. Um, as you can see, Pt.1b, Pt.1c, Pt.1d, all real planets actually researched. Now, red dwarf stars, of course, have less temperature and a very small size, but still they have good density and are able to attract planets. Now, the only problem with red dwarf stars is that they release a lot of solar flares, which could make habitability a problem, but usually it's not the case. Especially for this type, this star, it's not the case. Now, if I look at the planetary system, you can see all these planets that actually exist and they have their own information in space engine. It is thought that Trappist-1c, Trappist-1d, Trappist-1e are the planets that can actually have life. So if I go inside this, you can see you'll be able to see many things like mountains and gravel and soil. But that's not the main focus of the video. So yeah. So just like yellow dwarf stars, these stars also have many sunspots. Nothing much different about them. But yeah, this red hue is also the some matter is always shed by stars. But yeah, if we look at the system over here, we can see how the planets are. So many planets. If I look at this info, you can see real object. Even the planets, exoplanets, all real objects. If I go into this info, it shows real object, which makes it very interesting about how far the technology has come. That we are able to find planets outside of this, outside of our solar system, so far away, which makes it very interesting. Now I can look at it side by side as well. You can see like full size of planets, how they compare to the star. And if this was the sun, if the star was the sun, the planets would look like tiny dots. But this is the core of a star, and all these planets are quite comparable. You can see them compared to the star, which just shows how small the star actually is, even though it would look massive. Now, the last category, last type of star is known as a black dwarf. And this is quite interesting because there are no black dwarfs in the whole universe. There are no black dwarfs. Then how do we know that there's a black dwarf? So the age of the universe is 13.8 billion years. And although this sounds like a large number, it is quite a small number. And no star has been old enough to become a black dwarf. So black dwarf is a theory, but it makes a lot of sense because eventually red dwarfs have to cool down to zero because red dwarfs they don't have any nuclear fusion happening anymore. From the white dwarf stage, the star kind of dies, only the core remains, but it is not able to generate its energy anymore. It's just that it is so hot that it just radiates it away. Now, black dwarfs are stars that will have freezing temperatures of the space, absolute zero. So in trillions of years, maybe there would be a black dwarf. So that's what makes black dwarfs interesting. But yeah, with that, the types of stars, um, low mass stars are covered. And yeah, that's it.